Okay, thanks everyone for joining us today. My name is Nathan Fox from the Bryan Research Centre. I'm getting confused, I'm too excited. This is the final seminar in the JKMRC Friday Seminar series for 2021. Thanks for everyone to coming down today. We haven't had this big an audience since the start of my 10 years doing this, so thanks for coming down. It's glad to see a kind of an almost return to normality. Thank you also everyone for joining us today online. Before I begin, on behalf of the University of Queensland, we would like to acknowledge the traditional owners and their custodianships on the lands on which we meet today. We pay our respects to their ancestors and to their descendants who continue cultural and spiritual connections to country. We recognise their valuable contribution to Australian and global society. Well, it's a pleasure to introduce today's speaker, Dr. Grant Ballantyne, who is the Technical Director of Technical Solutions at Auscenco. Grant is well known around here. He completed his Bachelor of Engineering here at the UQ with an honours degree at the Department of Chemical and Metallurgical Engineering before beginning a PhD here at JKMRC, which he completed in 2011. Grant worked here as a research fellow until 2019. He was working on a range of different projects, which I probably don't need to remind you of, but it's certainly energy reduction, mineral processing and breakage models. In 2017, Grant was awarded the Minerals Engineering Young Person of the Year Award, and in 2019, he also won the CEEC medal. Grant is currently the Director of Technical Solutions at Zenko, as I mentioned, and he specialises in design, optimisation, operation, research and development. Grant coordinates the International Comminution Group, and he provides critical input at the front end of engineering design projects, so particularly focused on new technologies, including coarse particle flotation and bulk ore sorting. Today's talk, Grant's going to be talking about using techno-economic modelling to make investment decisions, which is going to be a very interesting topic. So before I hand over to Grant, for those of you online, questions can be in the question and answer box at the end, and we'll take questions from the floor afterwards. So Grant, thanks a lot, over to you.
Thank you. And can you hear me well enough? Yep. It's great to be back in this room. It's been a while since I've been here. Great to see so many faces that I recognise and friendly people that I get to talk to. So, yeah, the idea for today's seminar started off, I was going to be talking about kind of my personal journey into engineering from research. That became too hard to do. It's hard to reflect on personal things. So I instead have fallen back on something that's a bit more technical and a little bit easier to present. So today I'm going to talk about using techno-economic modelling to make investment decisions. This is something that I've been doing a lot of at Zenko, and I've really seen a lot of value in this way of approaching problems, in looking at the technical details, understanding the mass balance, the recoveries, all those kinds of things, and then overlaying on top of that the economics that allow you to then make those investment decisions. And when I talk about investment decisions, they might be buy a new piece of equipment, but I think from the researchers in the audience, it could also be investment in research. So if we do these kind of early assessment of the economics, the size of the prize, that could be the benefit of the technologies that you're looking at. That then allows you to get better a foot in to get the investment into those technologies. So I'll start the presentation. We always start our presentations at Ausenco's with a values moment, and this is a bit of a different one. And I had my final hockey farewell dinner a couple of weeks ago. And every year when we have our final dinner, someone gets up and does a toast to the game that we play. And I think it's a great way of talking about how great it is that we get to play this amazing sport that I play, it's hockey. And I thought we do this too infrequently in our field. I was talking to a colleague of mine, and we were Matt Pyle, and we were just discussing how fortunate we are to be in the position that we're in, and to be in the industry we're in, and to have a great career. So I thought I'd do, as my values moment, a toast to being a metallurgist. So there are a couple of images that are just going to pop up. I did a presentation the other day, and I'd collated a few images from over my career. But when I think about being a metallurgist, I think it's an incredible position to be. It's one of it's so global. You get to meet people from all around the world. I've got friends that have moved from down in New South Wales over to the Dominican Republic. Others moved from North Queensland over to Alaska. Others are in a place called Suriname, which I had to Google. There's mining in wide and amazing places around the world. It's probably because no one wants it in their backyard, and NIMBY syndrome. But that means that you get to interact with people from all around the world, and you get to see places that other people don't get to see. Another great part of being in this role is the influence you have over large decisions. In the last week, I found that I was in part of a group that was influential in someone making a multi-billion-dollar decision. That's amazing that we can actually be influential to that level. Another project in the last week just found out we were able to assist a company in increasing their production to the point of about $500,000 of copper per day. And so those kind of decisions and being able to actually influence people at a high level with the technical, I think is a great benefit of being in our industry. And I guess finally, the other thing that we get to do is be a part of the future economy of the world. I had a mate who bought a Tesla, and he said he bought a Tesla because he was in mining, and he wanted to support the mining industry because the Tesla's obviously has a lot of copper and runs off coal. So that was a bit of tongue in cheek, but we have an ability to be able to provide the raw materials, everything that isn't grown is mined, raw materials to benefit our society. And we can do that with technologies that reduce water, energy, and tailings, and can reduce the impact of that as well. And I think that's a really special place to be. So if we had a beer, I'd toast to being a metallurgist, but if you have any coffee cups, you can toast to being a metallurgist. There we go. So that's my values moment. So I thought I'd just start off this presentation by presenting something. I did a AusIMM webinar actually a couple of days ago. I don't know if anyone was able to see that. But in that I was looking at how technologies can impact ESG and sustainability. And when I think about the impact of technologies on ESG, I think of the three aspects of water, tailings, and energy as being the main ones that we actually have influence over. And what I presented at that meeting was that we can reduce tails intensity with a couple of different technologies, two of which I'll present today, pre-concentration and coarse particle flotation being the major ones. We can reduce tails intensity by over 50%. We can reduce water intensity by over 50%. And this really comes down to having a sand stream that is free draining that you can recover the water from. And we can reduce energy intensity, comminution energy intensity particularly. And the final technology there you can see is VRM, so vertical roller mills. And we can reduce that by over 70%. And this is with technology that's currently available. So, but what is the goal here? Is the goal just to reduce water or tailings and energy? Where is the value? Where is the value in these kind of technologies, in pre-concentration, coarse particle flotation. Is it in OPEX? Is it in throughput? Energy, water, tailings I've already talked about, but there's also recovery, resource recovery, grade, CapEx. There's so many different things that this impacts on. And if we focus on one of those things, there's the very real possibility that you'll have a deficit in another one of the areas. So how do we actually evaluate the value of these to mining companies? And that's really what this talk is going to go through. Now, when I started at Ausenco, Greg Lane gave me a book called The Goal by Eli Goldratt. Fantastic book if you ever want to read it. Yes, it does look like Simon Michaud's on the front cover, but it isn't. It's a fantastic book that goes through the journey of a manager of a manufacturing plant and the journey that they go through in optimizing the manufacturing plant. But it has a lot of crossovers into our world in mineral processing. Very short book, and it's written like a non-fiction. But what comes out of that is that the goal for this manufacturing plant is to increase throughput, which they talk about as manufactured out revenue at the end, so rate of revenue, while simultaneously decreasing inventory and operational expenditure. Now, that can easily be translated into mineral processing, and that is what I would suggest is the goal of what we do in mining, is to increase the throughput of metal that's sold at the end, while decreasing inventory. And you can think about inventory in a couple of different ways. I mean, stockpiling is one, but you can also think about CapEx there as well. And simultaneously decreasing operational expense. So that's pretty easy to understand. But what comes into the equation there is that you have these constraints and bottlenecks of a plant, and they are ore and equipment and flow sheet specific, and they control what throughput you can get at the different that you're able to achieve. And if I just overlay on this, if we look at a traditional SABC circuit, the bottleneck is typically designed in there to be the SAG mill. This constrains the throughput, the mass throughput, not the metal throughput, but we can talk about that later. And so therefore, we need to understand what the throughput is through that bottleneck, because that controls the overall economics of the entire processing plant. So in saying that, I think there's two different ways that we can influence the goal. Two main ones that I'm actually going to talk about today. The first one being increasing the ore grade through the bottleneck by taking advantage of ore heterogeneity or pre-concentration prior to the bottleneck, so prior to the SAG mill. And there's a number of different technologies that can be used here. I'll be concentrating on time and space ore heterogeneity that we take advantage of. There's abilities to do that on the shovel using X-ray fluorescence. Bulk ore sorting, large packet bulk ore sorting using prompt gamma neutron activation analysis. And then also high definition bulk ore sorting, magnetic resonance, so looking at the actual minerals. But there's a lot of other different technologies that can be used here, and I'll talk a little bit in more detail about that later. There's also size-based ore heterogeneity that we can take advantage of. And this is where the natural fragmentation of the ore fragments the higher grade into the fines. This is traditional grade engineering that CRC ore was promoting. And I think it's, and I'm really proud of a plant that I've been involved in the design of recently up at Ravenswood. It's actually currently getting constructed, and they're taking advantage of this size-based or natural deportment of value to the fines to be able to reject 40% of their mass and improve their water and energy efficiency and grade into the plant. And then there's more particle-based sorting that can be done using X-ray tomography or other such technologies. And then also coarse density separation, like what was happening up in Mount Isa, using dense medium cyclones. So there's a number of different ways that we can do this. I'm going to concentrate on the bulk ore sorting today and kind of put the actual technology to the side. But what do I mean by space and time-based heterogeneity? So this is the best way I could think of pulling it together. I actually put together some Lego with my kids. They enjoyed this process. But you can imagine the grade variability in space in an actual pit, red being high grade here, green being low grade. There's this natural heterogeneity around the deposit. Now, that then gets mined, dug up, crushed and put on a conveyor, and that spatial heterogeneity is converted into a time-based heterogeneity. There's some mixing that occurs in that process. And then that interacts with a technology that's able to divert the low-grade material off into a stockpile and increase the grade through the bottleneck. So this is the simplest way I could think of explaining it, and I think it does a good job with Lego. So how do we actually assess this in practice? Because it's very difficult to understand what the technology is actually going to be able to see. If you've got a greenfield plant, if you've got a brownfield plant, you can just put a sensor on the actual belt that just senses with time. But if you've got a greenfield plant, you need to understand the spatial heterogeneity, how that transfers into a time-based, and then how the technology interacts with that. So what we do at Zenko is we look at the grade of the grade variability down drill holes. And you can imagine each one of these bars is kind of a meter length of drill core. And the dotted line there is an average of 10 meters or so of drill core. And so the 10 meters of drill core actually represents what would be able to be distinguished using standard kind of drawing polygons on the pad and understand and digging to those polygons and traditional kind of grade definition of ore and waste. Whereas if we're able to get down to that smaller scale, maybe separating for magnetic resonance, able to separate every 2 seconds on the belt, we're able to see that underlying heterogeneity that sits behind that. And we can get an understanding of what actually is ore and what is waste. And you can reject some of those low-grade pockets that are within a higher grade larger packet size. So that's one data set. There's another data set. But what we do with that is we plotted on this, we do this release analysis, which has been done for a long time, where it has mass yield versus metal recovery. The parity there would be if all the mass and the metal went in line with each other. And the further away you get from that 45-degree line, the more separation occurs between the metal and the mass. And so the efficiency improves and also the size increases as you get close to the parity. So if we look at that initial assessment that I've got on the right there, you can actually plot that. You can take the standard approach where you average over the 10 meters, and then you take into account what would actually be occurring over those 1 meter intervals, and you can get that release analysis for that describes the in situ ore heterogeneity. Then you're able to apply some mixing that's occurring due to the mining method and the materials handling that happens downstream, and get an idea of what grade variability that sensor's gonna see. You can then apply that to a technoeconomic model, which is kind of what you're seeing here, where we've got tons per hour solids and relative copper percentage. And you can see what happens in the grade control, where you're measuring over those 10-meter increments versus in the bulk ore sorting, where you're able to measure over smaller increments. You can then understand what grade is being rejected and what grade, the upgrade that actually happens prior to the crusher and to the milling circuit. So I've got a couple of case studies on this. The first one is a Greenfields business case where it was very high level. We were looking at the grade control packet being about 10 kilotons, but the bulk sorter was able to sort over 2.5 tons. And we were able to look at the release analysis on the grade control accepts. And the NPV and the NPV on CapEx were very compelling. So when we did the economics on that, it was very compelling, and you can see how far that is off the parity line there. And actually, the payback period, because it's very low CapEx for this equipment, the payback period was very short, and it also increased. The benefit increased as the mine progressed. So that was a really interesting case study, but it was pretty standard. The second case study I'll present is a Brownfields expansion that was done. And here we were looking at a sorter that was actually throughput constrained. It was an offline sorting that was happening as kind of a testing equipment that then was coming into production. So it was a testing equipment to test the feasibility of bulk ore sorting, but then the benefit of it was seen, and they wanted that to include that into production. So really the benefit there was to bypass the sorter with the high grade material going straight to the mill from the mine, and the low grade material being bypassed straight to the stockpile. So the sorter only saw that kind of marginal material, and then the mass rejection was varied to optimize NPV. So we're able to pull that into the technoeconomic modeling. And that was the highest value was achieved by actually increasing the throughput, the revenue through the bottleneck, which was the mill. So once again, that goes back to what we were talking about as the goal in all of this. The third case study, and this is a really interesting one, where actually satellite underground deposits with long distance trucking to the plant. So the trucking actually became the bottleneck in the process. So although it was underground deposits, there was the ability to bulk ore sort those underground deposits and move to more of a low selectivity mining method, lower cost, low selectivity, and then do the selectivity above ground using the bulk ore sorter. And in this process, we had a look at the NPV as you change the head grade to the plant, and how the trucking costs actually associated with that. And we found that there was an optimal upgrade factor of 2, where the NPV was optimized, and above that point, the system was mine constrained. So yeah, really interesting little case studies there that show that the application of this is really case specific, and that there's real value to be found by linking the technical modeling with the economics to be able to optimize for the goal. The second way to improve the goal that I'm going to talk about today is to decrease the work done by the bottleneck. So in this presentation, I'm going to talk about coarse particle flotation, but there's a number of different ways that you can look at this. You can have, as I've talked about, most low value, high tonnage plants are designed to have the mill as the constraint. And sag mills can be deconstrained by rejecting pebbles, potentially if they have lower grade than the feed. And I've been working on a plant that does this down in New South Wales. And improved size separation can deconstrain the ball mills by producing a coarser product with similar downstream performance. So we can think about fine screening here or other technologies that can be used to produce a product that has a better distribution of material in the floatable size range. But what I'm going to talk about today and concentrate on is really coarse particle flotation. And this can deconstrain the entire comminution circuit by significantly increasing the grind size that can be while maintaining or improving, in some cases, the overall recovery. So the idea of that really is that you decrease the work that the bottleneck is doing, and that allows you to get a higher throughput at the end of the day, throughput in terms of metal produced. So what is coarse particle flotation? And I think there's a few experts in the room that will know most of what I'm talking about. It's actually a density separation device that has had bubbles put into it. So the bubbles attach to the valuable ore minerals and make them lighter. It's not a traditional flotation device that where there's a froth. It just makes those valuable minerals lighter and then does a density separation on them. So the image on the right there is actually the hydrofloated Cadia, which Ausenco designed, and first one in base metals. And if you look at the left, you can see how the technology is actually developed. There's a fluidization water and air are pumped in together, and there's a fluidized bed where the bubbles are attached to the mineral particles of interest. And then they rise up, and there's the density separation that actually happens above that. So what benefit does that have? As I said, it allows you to coarser the grind size without losing recovery. So you can see here some real data of what happens when you increase the primary grind without CPF, so conventional flotation systems. The recovery drops off dramatically. Whereas with coarse particle flotation, that recovery is extended out to much coarser sizes. And actually you start getting into constraints of the classification technology as to how coarse you can actually go in terms of the product from the milling circuit. So that's kind of highlights the benefit from a technical perspective. And now if I go through a couple of case studies, this first case study was a Brownfields expansion where we were comparing coarse particle flotation, and it included pre-crushing to be able to debottleneck the sag mill and allow the ball mill to grind coarser. And we put together a technoeconomic model that did the full mass balance of solids and copper around the circuit, and produced a NPV on CapEx graph, which you can see in the bottom right there. The bubbles there, the size of the bubbles is proportional to the copper production, and it just plots the NPV versus the CapEx. And you can see the difference between conventional expansion that they were looking at this plant versus the coarse particle flotation and the pre-crushing. Much lower capex required and much higher returns from the technology. What was key here is really getting this, the technical models of the coarse particle flotation, because there's a number of unit processes that you can see there, including classification and the coarse particle flotation. And so that modeling needs to be done from an assay by size perspective, including the densification factors in classification, and then using the basic Bazin style analysis is what we were using in this case. But I think there's some work being done here at the JK, looking at improving those kind of models that can be used as the underlying technical models that occur. In the second case study, we looked at where coarse particle flotation would be best positioned within the circuit. Now, the circuit on the left there has coarse particle flotation as in a scavenger duty, so following the rougher, same as what was considered at Cadia. But there's a lot of people wanting to put the coarse particle flotation in a pre-roughing duty in front of the rougher, and there's expected benefits from that. However, when we've pulled this into the technoeconomic and model and looked at the impact of densities around the circuit and what needs to be done around the water balance and a number of other key considerations, actually inputting the coarse particle flotation in a scavenger duty has improved benefits. And the graph on the right-hand side, you can see where I did a what-if analysis. I said, what if the recovery by size of the coarse particle flotation was variable? So it's a new technology. What if we start losing the ability to be able to recover, or the recovery drops, and there's variability in that recovery? And what I found is that variability impacted overall recovery to a much greater extent when it was in pre-roughing duty than when it was in scavenging duty. So there's a higher risk of not producing a throwaway tails when it's in pre-roughing duty than scavenger duty. So there's higher risk, and there's also higher capital to have it in that pre-roughing duty. So I've gone nice and quickly, so there'll be lots of time for questions. The key messages here are that, as I said, the goal in mining is to simultaneously increase the throughput of metal while decreasing costs and decreasing inventory. And I think MPV on CapEx is a good representation of that. And that's how we represent most of our results from this kind of analysis. And enhanced process technologies, which I was really talking about, are able to achieve this goal in two ways. So they can increase the grade through the bottleneck, or reduce the work done by the bottleneck. So that's the pre-concentration and the coarse particle flotation that we're really talking about there. And so in modeling the bulk ore sorting, we can translate the spatial heterogeneity to time and link that in with the technoeconomics to be able to provide a solution that can allow you to get that investment into that technology. And then also assessing the value of the coarse particle flotation requires models incorporating that assay by size information. And then all these models, these technical models, can be overlaid with the economic details of CapEx and OpEx to allow those investment decisions to be made in relation to the goal. And I think that's the key outcome from the work that we've been doing. So I'll end with just acknowledging two of my colleagues, Matt Pyle and Greg Lane, but also acknowledging the people in the room here that have been influential in my journey as well, and also just all the people that have assisted in this work. I think Tim Viscara worked on one of those case studies as well. So there's a few other people I need to acknowledge there. But thank you for giving me the opportunity to present today.
Thanks very much, Ron. That was a fantastic talk, and thanks for the personal touch as well. Obviously, you have a lot of history here, but great to see the technology being adopted at a lot of different scales of operation as well, which I think is really key. Questions, either in the room or online?
Grant and I always are the ones who ask questions straight away, so we have to ask each other. So, Grant, I really enjoyed your nice high-level, clear message you had there. So I'll go and pick at it, of course. Yes. You picked on the SAG, which is designed to be the bottleneck. And the more I've looked at them of recent, they're not the bottleneck, they're the perceived bottleneck. So the actions that are being taken are actually making the bottleneck worse. So, an example is huge SAG mill. The real bottleneck is the transfer point is the screen size, SAG screen, and the transfer from the SAG screen to the conveyor that recycles pebbles. So just within the way you're looking at the technoeconomics, how do you identify those? Because you can't identify them from data. How do you identify them, and then how do you put them in? Can you put them in a design and justify you should have twice the size of your screen, or a silly transfer point that no one identifies? They just put in the cheapest device there, as far as I can work out, and it's a bottleneck for the whole circuit. So it's a detail thing, but I'm finding the details and things like materials handling are more and more the bottleneck in the process.
Yeah, I totally get what you're saying there. And unfortunately with COVID and stuff like that, it's very difficult to get out to sites and look at those things in detail. I think what we do typically work with the operations. We do walk-arounds with cameras and those kinds of things, virtual tours, to identify those bottlenecks, because yes, they're not always easily identifiable from the data. I think Rajiv Chandramohan, who's an ex-graduate here, does a lot of that work as well in terms of optimization of plants and identification of bottlenecks. So yeah, we definitely do that. In terms of the design, as to designing the bottlenecks, I think that's probably poor design that's occurring there. Everything that we try and do is to make sure that those ancillary bits of equipment don't become the bottleneck, because that's where you start to lose value. And I guess we pride ourselves at Zenko at being able to produce low-cost plants, as you probably know, that with low concrete and low steel, half the concrete and half the steel over other plants. But we don't do that at the expense of the bottleneck, because then you just lose value. If you reduce the capex by changing your screen, you're going to lose value in doing that, and that screen's going to become your bottleneck. So yeah, I totally get what you're saying, and I think that's critical in the design phase, that those kinds of things are identified.
Yeah, I think the thing is having it in the techno-economic model, so it can't be value engineered out of the process, is the thing. So it shows up, because they don't show up is the problem.
Yeah, and one of the things I've learned with engineering is that you can, and I do a lot of front-end engineering, I don't do much of the back-end engineering, if you know what I mean. So I kind of set the project on its course and directive, but a lot of those decisions can creep in as the detail is added and as different voices become heard. and as the process kind of develops as it goes down, and you get into those detailed conversation, and you've got to have that review that comes back and says, why did you do that? That doesn't make sense. So yeah, I think that's key in how designs are put together.
Oh, well, we've got a whole bunch of questions online, actually, so I'll just read the first one. This is from Marcin. Thanks, Grant. Can you please say more about the issues with water balance when placing coarse flotation in front of the rougher? What's the key issue / problem, and what effect does it have on circuit operation?
Yeah, so the key issue there is that the hydrofloat concentrate has, say, 10 to 15% solids. And for that to be going into the rougher then causes residence time issues in the rougher, or if it goes into the cleaner, there's even greater residence time issues. So that has to be thickened, and that adds a lot of capital cost. When it's in a scavenging operation, you can put in a simple, cheap classifier cyclone that can, a dewatering cyclone that can then remove the cyclone overflow. If there are fines in there, they're fines that haven't been recovered in conventional flotation, so they're low grade and can produce a throwaway tail there. So it's really about the capital cost of these, of putting it in pre-roughing and post-roughing, and the water balance has an issue in pre-roughing.
Okay, thanks a lot for answering that. We have another question online from Paolo Lopez, just asking about, I'm wondering whether thickeners for concentrate and tailings are considered bottlenecks, and how much improvement can you make here, and what could be its economic benefit?
It's a good question. I'm not a thickening expert, but yes, I have seen them become the bottleneck. There are many different designs of thickeners that can be used, and rakes and feed well designs, and flocculants that can be used. I'd probably go and talk to Matt Pyle about those kinds of things to be able to get a better picture of it.
Okay, thanks very much. This might be a big question, but what do you think the highest primary PAT that a plant can process using a CPF process at a tailing scavenger application, assuming copper plant is not limited by, assuming and not limitation is not by liberation? If that makes sense.
Yeah, no, that makes sense. Yeah. So there's definitely some sanding issues that can happen when you get coarser, depending on your flotation technology. I mean, whether you're Wemcos or conventional float cell, there's different sanding potential of those different technologies. So that's something that needs to be taken into account. But primary to that, I think, is what the cyclones can actually achieve. How coarse can the cyclones actually go? To get to coarser than, say, 300 micron, you have to start running those cyclones very dense, and that causes efficiency issues in the classification. So there's some work about changing the angle on those cyclones, maybe adding screens around it as well, and doing a hybrid kind of classification that can get you much coarser. But I think the coarsest that I've seen a primary grind go was, I think, 360 micron, I think was I'd seen a P80 out of that when they were operating very, very dense. Yeah.
Okay, great. Thank you very much. I hope I can read this one a bit better. It's going a bit back more to the techno-economical considerations. A question from Darius Okel. Just wondering, in regards to calculating CapEx, MPV and payback periods, how are you treating changing economical parameters in that forecasting, for example, metal price forecasting over the payback period?
Great question there, Darius. It depends on the application, realistically. We normally try and use the same economic values that the client team are going to use to evaluate the project. So we try and get as close to that as possible. And that can change year by year. And we've done projects where we've changed the price year by year and changed and had the mine plan incorporated in the technoeconomics as well. So that really gets the what happens year by year out to the open. But yeah, we normally are led there by the client team and what they use as their economic parameters.
Okay, excellent. Thank you. Great. Do you have any other questions?
Enjoyed your talk, Grant. Thank you very much. Implicit in your talk and all the questioning and so on is risk. Yes. and uncertainty. And it's implicit. You didn't, and in fact, one of the downsides of this industry, it doesn't put error bars on things. Have you and your colleagues thought about explicitly dealing with uncertainties and risk management?
Yeah, so great question. Just yesterday, I was presenting the NPV on CapEx graphs with error bars incorporated in them for a client. So yes, we do, because some technologies have higher risk. What's interesting is that you can either incorporate that risk as a risk in recovery or a risk in OPEX or a risk in CapEx over that time. But actually, when you boil it down, it's just as easy to pull that down into a discount factor. So conventional technology might be 8% discount factor and new technology might be 10, which then gets you in a similar range in that risk. And you say, this is where it would be if it was 8, this is where it would be with 10. And that seemed to, at least for the project that I was presenting yesterday, seemed to align well with the error bars that we were looking at. So yeah, there's a number of ways of introducing that. As soon as you start multiplying all these risks, CapEx risk, OPEX risk, recovery risk, discount factors, it's meaningless. You get this, it could be anywhere in this massive circle that encompasses the whole world. So there's taking into account risk. And then there's also the other thing that we use for a lot of this is actually take the optimistic route and say, this is where the technology needs to get to. And this might be something good for research and saying that actually this is the hurdle that you need to get over to make this a viable solution for a plant. You need to be able to get 90% recovery using this technology, or else it's not going to pay itself off. So it's kind of a couple of different approaches there. But yes, we've done some risk on tailings dam failures and applying that to the NPV as well. And so environmental risks as well come into that.
Thank you. Sorry, I was just going to get on to another question, and then to Angus quickly. But there's a question from Narita Scott, just wondering, because you mentioned size by assay, and that's been increasingly used in a lot of test work. But the question is, as you trend towards the hindered settling and density-based separation systems such as HydroFloat, will we need to start considering the third dimension in terms of maybe assay by density as opposed to assay by size?
Potentially. Was that Nerida asking that?
Yes.
Thanks, Nerida. I didn't incorporate a density by size. It could very well be the third dimension there, rather than copper, for instance. What I ended up doing was saying, what is the density of the two components? So there's the sulfide components and then the non-sulfide gang. And I took that as the difference in density and then applied a densification factor on the classification. So it wasn't a smooth density distribution as such, which would have been a more precise way of doing the analysis. I instead used two systems a two-component kind of methodology, and I think it's accurate. Maybe not as precise, but accurate enough for what we're doing.
So, what would you go minimal by?
You can. I guess it's the increase in. Sorry.
So the question was, why don't you do mineral by size?
Yeah. So it's very easy to go into that way as well. The reason I do assay by size is because it's simpler and less complicated. And so in everything that I'm doing at the moment, trying to make it, trying to add value by getting accuracy correct without getting swamped by precision. If that makes sense. So without getting as precise and doing the exact right kind of scientific method of getting exactly within 10 decimal places, trying to get the accurate response rather than the more precise response.
So Grant, suppose you've debottlenecked your SAG mill using pre-concentration and coarse particle flotation, and Malcolm or Rajiv has spotted all the transfer points and belts that need to be sorted out. What do you see as the next bottleneck in the circuit? And do you have any technology on your horizon that you think might be useful for that?
Oh, next bottleneck in the circuit. So in terms of, I don't know whether it's really, that's a good question. I haven't thought about it enough. Other technologies that we're looking at are around leaching and trying to get a good understanding about sulfide leaching and those kinds of things. And I guess that comes back to the mine being the bottleneck and producing more value out of the waste material that the mine produces or the low grade material that the mine produces. Yeah, I'll come back to you on that one. I don't know an elegant answer to that at the moment.
Your next presentation.
Next presentation.
Okay, I've got a quick question. In terms of implementing the sorting technology, they can transform the economics of mining operations, but how early can we identify deposits that can be sorted economically? Are we doing enough at the test work stage and characterization stage of new mines so we can embed them into pre-feasibility or feasibility studies as opposed to try and retrofit them to mines that are currently operating?
Yeah, that's a good question. I think more and more people are doing these kind of heterogeneity assessment of the mine and greenfields, and really it's good practice to look at that up front and say what is the heterogeneity of my deposit? Can I include some kind of bulk ore sorting? It's probably, and I don't know whether the CRC ore guys would agree with me on this, but the grade deportment by size is very difficult to do, very difficult to assess in situ. The variability in space is easier to assess, and probably the particle sorting response is also easy to assess because that can just be done as typical test work. So there's probably levels of degrees of complexity there for the different technologies that can be applied. But yes, I think more and more companies are doing this heterogeneity assessment on the drill cores, which is good.
Excellent. Well, that's good. Thank you. Okay, do we have any other questions in the room? Got one at the back. Okay.
Hi, Grant. Thank you. Just got a quick question. You mentioned about the CPF that can reduce about 36% in energy intensity. The question is, that 36% is based on just like some sort of a theory things, or is that the case study? That's just a quick one. And the other one I've got, have you ever thought about the high voltage pulse or not? Thank you.
Yeah, so because a lot of the energy goes into the fine end of comminution, it's very easy to work out how much energy can be saved by coarsening up your P80. You can just do a bond calculation on that. But that's feasible. You can do it either as a calculation or you can look at it in practice. They're pretty well aligned. So in terms of, and so that's a reduction in specific energy, you should be aware. So you're probably aware that all of the reductions in energy and all the reductions in tailings and water were specific in that case. They were per ton copper out the end. And that's because if you've got an asset, a mill, it probably doesn't pay to have that mill half full in a lot of cases. So instead, if you're able to reduce the bottleneck, you then fill it up again. Maybe this comes back to Angus's question as well. Actually, when you reduce the bottleneck, you just fill it up again and it becomes the bottleneck, and you run to that bottleneck. It's still the most appropriate spot for the bottleneck to be. There'll always be a bottleneck, and it's about having that bottleneck in an appropriate spot. So that's where the energy comes from. The other question was high voltage pulse. Yes, when I was here, had a lot to do with that and understood and did some analysis on that. I think it's a interesting technology. When it's combined with the screening, I think it does the pre-concentration. I think there needs to be some more thinking around the pre-weakening that occurs from that. And the value proposition of that technology really needs something like this, where you do a techno-economic analysis on it. I haven't seen that yet done, but maybe I'm missing out on the publications.
Okay, great. Thank you. Thanks for the questions. There was another question online, but I might direct that to you afterwards because it looks a bit maybe very technical each slide. So, well, I just want to thank you one more time, Grant. Thanks for the seminar today. Thank you. Just as an announcement, next week is the ECHA holiday, so there's no seminar, and that's going to bring the seminar series to an end because we're kind of hitting the end of semester. So I think it's going to be back in probably February next year. All right, thanks everybody.